And this week we'll be working with metamorphic rocks. So a metamorphic rock is rock made up of a pre-existing rock. The pre-existing rock is called a protolith. It's a parent rock. And it's called that way because it's the initial stage of the rock before it becomes a metamorphic rock. So a protolith could be igneous in nature or sedimentary or even another metamorphic rock. So then what happens is the protolith, or the parent rock, is subjected to immense amounts of heat and pressure, which causes physical and or chemical change to the rock itself. And afterwards, the rock is cooled and we have our modern day metamorphic rock. So for example, we will have a piece of granite, and once we apply heat and pressure to it, and depending on the amount of heat and pressure, we will undergo metamorphism, and the end result would be something similar to a gneiss. So we can see the same type of minerals that are present. We have some of the micas that are present in the gneiss, and those show up as the black specks. Some of the feldspars in the quartz will melt and or partial melt, and we'll have those white banding in the gneiss. So some common use cases for metamorphic rock would be primarily for decorative purposes. So we have roof shingles here made out of slate, and as well as statues that are carved out of marble. And metamorphic rock is generally used in this sense because it's strong. It's a lot stiffer and harder than the parent rock, just because it's undergone such immense amount of heat and pressure, and it's for some of the material it's hardened the protolith rock. So in metamorphic rocks we have what's called foliation, and this is and we also have non-foliation. So the layering that occurs in metamorphic rocks is called foliation, and this is generally occurs in a type of zebra-like pattern, zebra stripes, and or something similar to a one cleavage plane, if we recall from our minerals lab. So when a rock doesn't have any type of layering or foliation, it's called non-foliated. An example of non-foliation would be this quartzite piece right here. So quartzite would, the protolith of quartzite would be more of a quartz sandstone, and when you subject that to a lot of heat and pressure, those individual grains of quartz in the quartz sandstone would partial melt and bind with one another, and you would end up with a quartzite, which generally has a lot harder properties than quartz itself. So quartzite will very easily scratch glass, and also has a very sugary, icy look to it. So some types of foliation that we would observe in metamorphic rocks is slaty, or also called slaty cleavage. And this is seen in slate and phyllites. And this is quite similar to the mica's one direction of cleavage that we saw in minerals. However, of course, we can see from this image here that the cleavage plane is not as pronounced and smooth and reflective as minerals, because minerals we're looking at molecules of the same type. This type of foliation is this type of slaty foliation is created through heat and pressure, and is more of a physical thing than a molecule bond thing as we see in minerals. Another type of foliation we see is schistose or schistosity, and this type of foliation is seen in schist, of course. So it's definitely not as flat or planar as slaty foliation. However, we do see that it does break off cleanly along certain planes. However, those planes are sometimes rather wavy in texture. We do see sometimes that garnets would tend to appear, as we outline them in red right here. See some little bits of garnet that pop up and appear. And I think we have a couple elsewhere in other places as well. So when we have garnets that occur in schist, there's a slight name change or an abbreviation to the name, where instead of a regular schist, we are now observing a garnet schist. And finally, we have Nisos or Nisosity type of foliation, and this of course occurs in the metamorphic rock gneiss. So in the metamorphic rock gneiss, what we normally see is this black and white smear banding that occurs, and it looks pretty similar to like a zebra stripe pattern. The rock will not break along these cleavage planes. Very rarely will it do so. And generally it is very hard, and we will have more of a conchoidal fracture along with the metamorphic rock gneiss than something that breaks off of the foliation planes such as schist or slate. And of course we have non-foliated metamorphic rocks. The two examples we have shown here are amphibolites and quartzites. We can see from this image that these two metamorphic rocks do not exhibit any type of foliation at all. There's no real distinct planar pattern with these rocks. The amphibolite on the left seems to have a very random, chaotic pattern. And that's from the metamorphism that has occurred to it. And the quartzite itself has no real pattern as well. It has a very conchoidal type fractures, and it does look sugary in appearance. So we have some general tricks to identifying non-foliated rocks. One of the first tricks would be to identify some of the minerals that are in it. For example, if we're able to identify garnet in the garnet schist, then we can safely assume that we're looking at garnet schist. Or if we can see some micas in our rock material, then we know what we are looking at could potentially be a gneiss. Or if we identify quartz in the quartzite, then we know what we're looking at would be a quartzite. We want to run tests similar to our mineral tests, such as the hardness, and use hydrochloric acid. So hardness would be useful in, for example, discerning between a quartzite and a limestone or a marble. So a marble being the metamorphic rock of limestone, which would tend to look very similar to a quartzite. So we can run a hardness test on it, since quartzite will scratch glass and marble will not, and also a hydrochloric acid test, since the marble is a metamorphic rock of limestone, which is a carbonate rock, which will indeed react with hydrochloric acid. So there's certainly different levels of metamorphism, depend on how much heat and pressure a protolith or parent rock is subjected to. And so there would be a gradient to no heat and pressure to immense heat and pressure. So that would be our metamorphic grade. And it's a measurement of how metamorphosed a rock is. So the higher the grade, the greater the deformation. So this goes from low to high, of course. So in the low grade, for example, we have slate, medium grade, we have phyllite and schist, and the high grade we have gneiss. Right. So for example, we have our protolith and metamorphic rock. We have a shale that would eventually turn into a slate when it goes undergo low-grade metamorphism. However, when we have high-grade metamorphism, we can potentially take a metamorphic rock such as phyllite and metamorphose it into the metamorphic rock gneiss. So with a mystery metamorphic rock sample, we want to make some initial observations. Do we observe foliation? And what are the grain sizes if you are able to see it? And do we see any distinctive minerals or distinctive features with our metamorphic rocks? And this should help us in identifying what type of metamorphic rock we are looking at.